Welcome to the second video of week 3 of this introductory course on synchrotrons and X-ray free electron lasers. Now, in the first video this week, we covered basics of the electric and magnetic fields acting on electrons and, by heuristic arguments, showed that accelerating electrons causes them to radiate light, of which synchrotron radiation is just one example. The characteristics of synchrotron light were shown to depend on several parameters, including the electron energy and the magnitude of the centripetal acceleration. We begin the second video by investigating this aspect in more detail. The bending magnets used for this and other elements associated with the storage ring, comprising together the so-called magnet lattice, are described in more detail. Lastly, we show how the energy lost by the electrons because of their emission of light is replenished in a radio frequency cavity installed in the storage ring. Now let's begin by considering how we steer electrons in a closed path. The electrons must experience a centripetal force acting at right angles to their motion in order to maintain them on a closed orbit. Note that this force need not be applied along the entirety of the storage ring, but can be broken up with straight sections in between. Remember indeed that third generation synchrotrons are defined by these straight sections, as it's here that the insertion devices are placed, which provide the most intense sources of X-rays. We'll talk about these in detail next week. For now, let's concentrate on getting those electrons on the closed path. The centripetal acceleration is A equals v squared upon rho, where v can be very accurately approximated by c, the speed of light, and rho is the radius of the bending orbit. Note also that because the electron is travelling at relativistic speeds, its mass, from our perspective, is gamma times its rest mass, which we've already established typically increases the rest mass by several thousand. The force is therefore gamma m multiplied by c squared upon rho. Two at first obvious candidates come to mind for imparting the centripetal force: an electric field, such as also used in old-fashioned cathode ray tubes in TVs dating back to the end of the 20th century, or magnetic fields, such as used for electric motors or loudspeakers. Let's first consider the use of an electric field. First, don't get confused with E here with the energy of the electron. E here actually means the electric field strength or amplitude. As we will see in just a moment, we can discount the electric field as a reasonable candidate for steering electrons. So let's tolerate this slight ambiguity for the meantime. Now, if one plugs typical values for rho and gamma into our force equation, and using the known values for the physical constants of m, c, and e, we obtain electric field strengths which must be of the order of 1 billion volts per meter to do the required job of the centripetal acceleration. But the breakdown field strength of dry air at 1 atmosphere is approximately 3 million volts per meter, over 2 orders of magnitude weaker, while that of pure silica is up to maybe 40 megavolts per meter. So it should be clear that using electric fields as a steering mechanism is impossibly hazardous. This now leaves us with the Lorentz force of magnetic fields. In the last video, we established that this is equal to EVB, or for our highly relativistic electrons within the storage ring, approximately ECB, assuming that the magnetic field points perpendicular to the electron's motion. Equating this to gamma m multiplied by c squared upon rho, the centripetal force, and then rearranging this equation, we see that the bending radius rho equals gamma mc divided by EB. But gamma mc squared is equal to the electron's kinetic energy, E. Hence, rho is equal to E divided by CeB. We can re-express this in practical units such that rho in meters equals 3.3 times the storage ring energy expressed in gigaelectron volts, divided by B given in Tesla. Hence, an electron traveling in a horizontal plane that experiences a constant B field acting vertically will be steered in a circular path of radius rho. From our practical expression for rho, we see that a few gigaelectron volt storage ring containing magnets with field strengths of the order of 1 Tesla will bend electrons along a path with a radius of the order of 10 meters. The fan of radiation in the horizontal plane will subtend the same angle as the arc of the bending magnet itself. Only a small angular fraction of this passes through an aperture to a bending magnet beamline. Because the fan angle is so much larger than the typical acceptance angle of a bending magnet beamline, more than one bending magnet beamline can be served by a single bending magnet. Now, what are typical magnetic field strengths? The Earth's magnetic field varies considerably, but is strongest close to the poles and can reach around 60 microteslas. Indeed, it is the combination of this higher magnetic field strength and energetic charged particles from the solar wind, primarily energetic electrons, that generate the aurora as these particles are funneled by the Earth's magnetic field to the polar regions, where they collide with molecules in the upper atmosphere, causing them to fluoresce. At a more mundane level, typical kitchen magnets have field strengths approximately 3 orders of magnitude stronger. The soft iron permanent magnets used at synchrotron bending magnets are 1 to 2 orders of magnitude stronger still, at around 1 Tesla. Significantly high fields can be achieved using cryogenically cooled superconducting intermetallic compounds, such as niobium-3 tin, shown here, which needs to be cooled to less than 18.3 degrees Kelvin, above absolute zero, in the form of coil windings in superconducting bending magnets, or superbends. As we will see very shortly, increasing the magnetic field strength can bring substantial benefits, particularly for experiments demanding high photon energies at low or medium energy storage ring facilities. The spectrum and intensity of bending magnet radiation depends on several parameters. Firstly, we need to know the angular frequency of the orbiting electrons, that is, how many radians per second they rotate during those times that they are being redirected by a bending magnet. To simplify the determination of this, let's assume that the orbit is perfectly circular, although even for real storage rings consisting of straight and bent sections, the result holds true. The orbit circumference is simply 2 pi rho, and a relativistic electron with a velocity close to c will thus execute c divided by 2 pi rho revolutions every second. But each revolution contains 2 pi radians, because there are 2 pi radians in 360 degrees, obviously. Hence, the number of radians swept out per second is 2 pi c divided by 2 pi rho, which is simply c upon rho. Inserting typical values into this, we obtain an angular frequency for the storage ring electrons of the order of 10 to the 7 to 10 to the 8 radians per second. The critical frequency is a value associated with the synchrotron radiation spectrum, not the electrons, although it is determined by the electron's energy and the bending radius rho. Now it emerges that this is equal to 3/2 gamma cubed omega 0. We can re-express this either by substituting omega 0 with c upon rho, or indeed, one step further, by remembering that C upon rho is equal to EB upon gamma m, which we discovered a little earlier in this video, when we equated the Lorentz and centripetal forces. This leads us to the expression omega c is equal to 3/2 gamma squared EB over m. Inserting typical values into any of these equivalent expressions yields a critical frequency of the order of 10 to the 19 radians per second. Now, if we multiply this by h bar, we obtain the photon energy associated with this critical frequency. If we convert this to electron volts, we obtain photon energies of the order of 4 kiloelectron volts. In actuality, this can vary strongly due to its square dependence on gamma, the Lorentz factor describing the storage ring energy, plus its linear dependence on B. To repeat, the critical energy is linearly proportional to B and varies with the square of the storage ring energy. A practical expression for this is provided here. For a given magnetic field strength, a bending magnet at spring 8 will have a critical energy some 18 times greater than the same magnet at the ALS, as the ratio is simply the square of their storage ring energies, that is 8 gigaelectron volts divided by 1.9 gigaelectron volts, all squared. The red dots show the critical energy for two bending magnet beamlines at the two high-energy storage rings spring 8, 8 gigaelectron volts, and the ESRF, 6 gigaelectron volts. In order to compensate for their more modest electron energies in the storage ring, facilities such as the Swiss light source, which has a storage ring energy of 2.4 gigaelectron volts, and the advanced light source, 1.9 gigaelectron volts, have installed superbends, shown here as blue dots, in order to access higher photon energies that would otherwise be impossible using normal bending magnets. But what precisely does the critical energy describe? From our discussion so far, it is probably already clear that it is somehow linked to the bending magnet spectrum. Before this is shown explicitly, let's have a little think about what we might expect the radiation spectrum from a bending magnet to look like, at least qualitatively. You should remember from the first video this week that an electron undergoing sinusoidal acceleration from a harmonic driving force, such as, for example, the electric field component of an incident X-ray beam, will re-radiate light at the same frequency. In other words, the electron scatters the incident light elastically. It has the same frequency. This is the Thomson scattering we were talking about. Now imagine an observer of the electron tangential to the bending magnet. From her perspective, the electron is first moving along the straight section upstream of the bending magnet with constant velocity. It's not being accelerated, so we shouldn't expect her to see any radiation, and indeed she doesn't. But once the electron enters the gap between the dipole of the bending magnet, it experiences a pulse of centripetal acceleration towards the center of the ring due to the magnetic field. In contrast to the case of sinusoidal acceleration, this pulse of acceleration can't be described by a single frequency, but instead is composed of a continuous spectrum of frequencies, and the electron will emit this in response. For the more mathematically predisposed of you, you might recognize that the spectrum that emerges from this pulse of acceleration is proportional to the Fourier transform of the temporal description of that acceleration. Now, for those of you less familiar with such insights, don't worry. As a consequence, we can expect the bending magnet spectrum to be broad. Shown here are three curves for different storage ring energies and magnetic field strengths. Note that the only difference between the spectra for a 1 Tesla bending magnet in a 4 gigaelectron volt ring and a 4 Tesla bending magnet in a 2 gigaelectron volt ring is the intensity, and this differs from each other by a factor of 4. Their critical energies, highlighted as circles, are identical, as the product of the square of the storage ring energy and the magnetic field strength are equal. Note again that high-energy storage rings, such as shown in blue for a 6 giga-electron-volt facility, easily access high critical energies on account of the square dependence on the storage ring energy. It turns out that half of the integrated radiative power produced by a bending magnet lies below the critical energy and half above. But what we haven't yet discussed is how the spectral flux is spatially distributed in angle and position. In general, the center of the cone of radiation is the most intense and most blue shifted to high photon energies. As one moves off axis, the radiation becomes weaker. Remember that the beam only has a width of approximately plus or minus 1 upon gamma of the order of 100th of a degree, plus minus. And the maximum is red shifted to lower photon energies, the maximum energy. Obviously, in the case of bending magnets, for which the horizontal angular spread is equal to the angle subtended by the magnet and is measured in degrees, the fan of radiation in this plane at the beamline is determined by the opening angle of the aperture to that beamline, which is always much smaller than the fan angle, but on the other hand, also much larger typically than 1 upon gamma. The total integrated radiative power output of a bending magnet is given by the equation shown here, where L is the length of the electron path passing between the magnet poles. As the entire storage ring requires bending magnets to provide a closed orbit for those electrons, the entire power output of all the bending magnets together in a storage ring is given for a length L equals 2 pi rho, where rho is the bending radius. Note again that this is not equal to the storage ring circumference, as the bending magnets are separated by straight sections. Now, there's also radiative power production by insertion devices, which we'll talk about later in the straight sections. But here, we're concerned only with the bending magnets. So, for example, a 3 giga-electron-volt storage ring using 1 Tesla bending magnets will have a bending radius rho equals 9.9 meters, for which 2 pi rho equals 62 meters. If we take an electron current of 0.4 amps, the total power output due to bending magnet radiation will be 283 kilowatts. Now, any one bending magnet port may only accept, for example, approximately 5 milliradians of this, or less than 1,000th of 2 pi, or in other words, 225 watts. This is further monochromatized to select a very narrow band of photon energy, as is more often than not the case. Perhaps only of the order of 10 milliwatts may then remain. This might not seem very much, but actually it equates to, for example, approximately 10 to the 13, 10 kiloelectron-volt photons per second, several orders of magnitude more than can be provided by laboratory-based X-ray sources. To finish this video, we will now consider the ratio between the power consumption caused by the generation of synchrotron radiation, which we have just calculated to be of the order of 300 kilowatts for bending magnet radiation alone, and might be double this when the insertion devices are also accounted for, and the stored power of the electrons circulating in the storage ring. The stored energy is simply their kinetic energy, or storage ring energy E, multiplied by the number of electrons within the ring at any one time. Now, this latter amount is simply the current in amps divided by the elementary charge of the electron and multiplied by the storage ring circumference, big C, and then divided by the speed of light, little c. This turns out to be of the order of 10 to the 12 electrons. Hence, the stored energy is approximately a kilojoule. The stored power is simply E multiplied by I, and this is measured in gigawatts. One might therefore think that the power loss through radiation is relatively slower, as the radiative power is 4 orders of magnitude smaller than the stored power. However, it only requires a small deviation from the nominal storage ring energy for an electron to enter an unstable and open orbit. It will spiral into the inner walls of the ring. Hence, the electrons require a steady replenishment of this lost energy. We finish this video by discussing this aspect now. Inserted in the storage ring is a radio frequency cavity, running typically at a few hundred megahertz. Within this resonant cavity, the electric field oscillates sinusoidally from pointing in one direction to the other. Now, along the central axis, this means the electric field is either opposite to or in the same direction as the electron path. Now remember, an electron is accelerated when the electric field points in the opposite direction to the electron's sense of motion, due to the electron's negative charge. Therefore, an electron entering the cavity when the field points maximally in the upstream direction will cause the electron to be maximally accelerated, as shown schematically in the figure on the left. Now let's consider two electrons, one of which, A, has a little less energy than the other, B, due perhaps to the fact that it has emitted a couple more photons in the last circuit around the storage ring. B, therefore, enters the cavity first and is accelerated by the cavity's field. Electron A enters a little later, at which point the field amplitude has increased in its sinusoidal cycle by an amount just enough to accelerate it to the same energy as electron B. If the electrons had entered the cavity at a significantly different part of the radio frequency cycle, the acceleration, or indeed perhaps deceleration, they would have experienced would have caused them to become still less stable in their orbit, and they would soon be lost. From this, it should be apparent that only a very particular time window of the RF cycle is suited to bringing the electrons back to the nominal storage ring energy. As a consequence, the electron current in a synchrotron isn't continuous, but instead is composed of bunches, each separated by 1/f, the period of the RF cycle, and having a temporal width of approximately 1/100th of their separation. It's a trivial exercise to show that the number of electrons within any one bunch is equal to the current divided by the product of the RF frequency F and E, the elementary charge. And this turns out to be of the order of 10 to the 9 to 10 to the 10 electrons per bunch. To summarize this second and last video of the third week, we have reasoned that only a magnetic Lorentz force is a reasonable way of steering electrons into a closed path in a storage ring. The characteristic or critical frequency omega c and the associated energy EC is equal to h bar omega c were determined and shown to depend on the square of the storage ring energy and linearly with the bending magnet field strength. The radiative power generated by bending magnets, and thus by the whole storage ring, excluding other components such as insertion devices, was determined and shown to be a small fraction of the power stored within the ring. Nonetheless, losses associated with radiation production need to be replenished, and the mechanism by which this is done, namely the use of a radio frequency cavity, results in the electron current separating out into bunches with bunch durations approximately 2 orders of magnitude shorter than their separation. Next week, we define the important photon beam parameters of flux, emittance, and brilliance. We further discuss components of the so-called magnet lattice, namely double and multi-bend achromats, quadrupoles, and sextupoles, and insertion devices, in particular undulators. The use of multi-bend achromats in so-called diffraction-limited storage rings, or DLSRs, defines the next generation of synchrotron facilities and is discussed in some detail. Lastly, we provide an overview of X-FEL physics and architecture and the radiation it produces.